While the geospatial vector model is based on point, line, and polygon features, the geospatial topological model is based on edge, junction, and connection elements. And those elements are represented on the slide as orange for edges, blue for junctions, and red for connections. And you can see it illustrated in the diagram along with the corresponding table. So for example, the edges are diagrammed as A, B, C, D, and E and represented in the table with the attributes edge ID, from junction, and to junction. So for example, edge B connects junctions 2 and 3. The junctions are represented in the diagram as 2 and 3, and in the attribute table also represent the turn. So the adjunction allows the movement from one edge to another. The corresponding turns restrict the movements. So in this example right here, the turn Y is illustrated in the diagram and represented in the table to restrict movement from edge E to edge B. So in the diagram, connection Y restricts movement from edge E to B via junction 2. You cannot move from edge E to A or E to D. Now, edges are elements over which resources flow. They're represented in GIS as a line feature class, and they're connected via junctions. The flow is the direction an agent traverses an edge, and it can be either along the digitized direction of the edge, from the beginning node to the end node, or as designated by an attribute of the edge. Some examples include two polygons that share a coincident boundary. The coincident boundary is referred to as an edge. Or water flows along a stream. In this case, the stream is the edge and the water is the agent that flows along the stream. Or vehicles drive on a street. Again, in this example, the street is the edge and the vehicle is the agent that traverses the street. Junctions are elements that connect edges. They're represented in a GIS as a point feature class. Examples include 3 lines share a common node. In geospatial topology, that node is referred to as a junction element. Water flows from a stream into a river at the confluence. In this example, the water flowing along the stream is the agent flowing along the edge and transfers from one stream to the river at the confluence, which is the junction. And last, vehicles turn from one street onto another at an intersection. In this case, the street is the edge that is connected by the intersection or the junction, and it allows the agent, which is the vehicle, to turn from one street edge to another via the intersection or junction. Last, connection elements define the movement between 2 or more edges via a junction. They're represented in a GIS transportation network as a rule in the transportation network, what we refer to as global turns, where when you reach an intersection, you can turn on any connecting edge, or a line feature class in a transportation network, where the turns are restricted to one of 4 options: right, left, straight, or U-turn. So you could have an intersection that has 1, 2, 3, or 4 modeled turns as a line feature class. Connections can also be represented in a GIS utility network as an attribute of an edge network element. We'll talk about the difference between transportation networks and utility networks in just a bit. Some examples of connections include movement from one edge to another is restricted or enabled. So the junction allows you to move from one edge to another, but the connection can restrict or enable that turn. Vehicles must turn right when entering a T intersection with one-way traffic. In this example, we don't want to use global turns where you can go from any edge to any edge through a junction. We want to restrict the turns so you can only take a right-hand turn. Last, water flows from streams into rivers. In this example, water always flows from the streams into rivers, never from rivers into streams. And so we can use connections to model that relationship. In ArcGIS, we create and maintain topology using 5 different approaches: coverage, ad hoc, network, geodatabase, and map topology. And we'll talk about each of those in just a second. Which topology you use depends on the type of data you're using, the relationship you're trying to model, maybe the software that you have defines which type of topology you can use, or the analysis you're performing is only supported by a particular type of topology. Coverage topology is a formal topology stored in an ESRI coverage. And an ESRI coverage is the original vector model that was released with ArcInfo in the early 90s. In some ways, coverages were replaced by shapefiles, and shapefiles were replaced by geodatabase feature classes. Now, coverages are similar to a file geodatabase in that it's a collection of files and folders that store geometry, attributes, and indexes. The limitation on coverages is that it would only store points and lines, or what were referred to as arcs and edges, but it didn't store polygons. The polygons were actually created in ArcInfo by building topology from lines and points. And if you look at the example on your right, you can see where I'm utilizing points and lines to build the grid of 9 polygons. And so if I wanted to update those polygons, I would first have to update the line coverage and then rebuild the polygons utilizing topology. Now, a big benefit of the coverage model is that it enabled something called spaghetti digitizing that we still utilize today. And again, if you look at the illustration on the right, you can see that the line feature classes actually extend beyond the polygons. And so you could sloppily digitize a bunch of lines and then build polygons from those digitized lines that were really precise. And you can see in this example right now, I've got all those little lines that extend beyond the polygons, but when I build out the actual polygons, they build very cleanly. This is referred to as spaghetti digitizing. Ad hoc topology is an informal topology maintained by the user, not the software. In ad hoc topology, the edits should respect the relationship between points, lines, and polygons, and it's only enforced by the user, not the software itself. The problem with this is that it can be really error prone. The user often makes mistakes, and that, of course, gets incorporated into the features that you're digitizing. It also requires twice as many edits as formal topologies. If you look at the illustration on the right, you can see that to edit the 2 polygons with the shared boundary, I actually have to edit 4 different vertices. And so it's not very efficient. It would be much more efficient if I could just edit the single coincident boundary between the 2 polygons. Now, unfortunately, ad hoc topology is the most common form of GIS topology. For example, again, I'm maintaining the boundary between Texas and Oklahoma, and I move the Texas boundary. I know I also need to move the Oklahoma boundary to match the Texas boundary, but the software is not enforcing it. I am if I'm using ad hoc topology. We use network topology to model real-world spatial relationships between geographic features. Now, participating features must be stored in the same geodatabase feature dataset, and that's because the feature dataset enforces a common coordinate system on all of the feature classes that are within that feature dataset. Network topology includes utility networks, which are referred to as directed networks. Directed networks are where the network directs the agent that moves between the edges. Transportation networks, which are also referred to as undirected network, in which the network does not direct the movement of the agent. The agent chooses its own path through the network. And also more specific networks like parcel fabrics and terrains. Parcel fabrics are used by appraisal districts to manage ground control, lots, and parcels, all within the same topology. So if I move or establish a more accurate ground control position, the corresponding lots and parcels would also change. Terrains are a form of triangulated irregular network that are stored in a geodatabase. So the points and the lines that connect the points, which make the faces of the triangles, those are all stored in a network within a feature dataset. Now, when working with network topology, connectivity is updated incrementally with each edit if you're working with a utility network or on demand with transportation networks. What that means is if I edit a utility network that includes, for example, wastewater lines, then the underlying topological network is automatically updated. But if I edit a street network where I create a new bypass around a town, I have to go in and build the underlying topology to reflect the change in the transportation network, and that's referred to as on demand. So I have to actually make the change and then on demand, or when I want to, rebuild the underlying topology. Geodatabase topology is a formal topology stored as a data object in a geodatabase. Like network topology, participating feature classes must be stored in the same geodatabase feature dataset, again, so that the geodatabase can enforce a common coordinate system on all the participating feature classes. Geodatabase topology consists of a set of integrity rules and feature class behavior. So for example, parcels cannot have any gaps or overlaps. And we want this when we're modeling parcels, because if you have overlap in parcels, that means two owners can own the same strip of land. Or the opposite of that, there's a gap between two parcels. It means nobody owns that gap. So we use topology to make sure that parcels have coincident boundaries. Another example of geodatabase topology is making sure that contour lines cannot intersect themselves. You can't have a contour line that represents 200 feet and another contour line that represents 210 feet and that they intersect, because you can't have a location on the earth that is both at 200 and 210 foot elevation. And so we can use topology to model that relationship. The last example is bus routes must be coincident with roads. The idea being that the buses must drive on the roads. So if you're representing buses as a line feature class in your GIS, the bus route lines must be coincident with the roads on which the buses drive. Now, just creating geodatabase topology is not enough. The geodatabase must be validated against the features to discover any topological errors. So you have to create the geodatabase topology, and then you have to validate it to discover any features that actually break the topological rules you've specified. So in the illustration on the right, we can see that we've established rules where polygons must have points, lines must not have dangles, and lines must be covered by polygons. And when you validate those topological rules against the features in the illustration, you can see how the topological errors are flagged. Last, map topology is a temporary topology that allows shared editing of spatially coincident features. It stores the edges, nodes, and vertices of the features that fall within the current display extent. And then you can use that temporary topology to perform shared edits. So for example, in the illustration on the right, you can see how instead of editing 4 different vertices to move the shared boundary between the two polygons, I can just either move 2 vertices for the shared edge, or I can even just move the edge itself. This allows for much more efficient editing and can reduce errors when editing as well. Now, map topology is not unique to geodatabase feature classes. It can also be applied to shapefiles that are stored in the same folder. And a nice thing about map topology is there's no rules and no validation process. You just enable map topology and then edit shared geometry.